All right, so you just made it through your first confidence interval example. Congratulations. We're going to give you a round of applause. You did one for 50% and you did one for 90%. And if you didn't do it, that means you didn't watch the previous video. So you need to go back and you need to watch it and you need to work it and you need to make sure that you can get the same answers as we did. Because if you can't, you won't be able to do it on the assignments or the test questions that are coming up. So, confidence interval. Well, we talked about one of the reasons to use a confidence interval. All right, so what we've done is that we have taken a sample in the lab and we report that value with a window. And that window is the confidence interval window. And that allows us to give us a range that we can report to a client or a company to say the true value lies within this window. So that's one of the reasons that we use confidence limits the way that we do. All right, but there's multiple other reasons why we use confidence limits, or why we use confidence limit. And the second version is that I can order a standard. And the standard can come from NIST or ASTM. And the lab will order it. And the lab will give the lab workers the standard. And this has an accepted value to it. And they know what that accepted value will be because it comes with a certificate of analysis, a COA. Right? That's another term that we learned about. And that certificate of analysis will have a stamp and it will say, this sample should be this amount. Bam! So the lab would give the sample to their lab workers. They would allow them to test the sample. So lab workers test multiple times. They will report a confidence interval or a window, and the lab will compare these two values. That way they can double check to make sure that you are doing what you're supposed to be doing and that you're doing it the correct way. They can trust your numbers on all the other samples because when you did this to the standard that they ordered, it worked out properly. So this is a way for a lab to double check your work. So that's number 2. Lab can double check your work. But you know, we always put the blame on you. It can also put the blame on the method. They want to make sure the method is working correctly as well. So that way, if they've changed something up in the method, or they are doing a new method that they've never done before, and they want to make sure that it's making sense and the data is actually coming together the way it's supposed to, well, they can use a confidence interval to make sure that that is happening the proper way. And again, most of the time, it is the 95% window that we use. We are 95% confident that the true value lies within this range, and hopefully if we're done it the right way, those numbers will actually begin to talk to each other and make sense. So here's an example of another reason that we would use confidence interval. Just another different type of example to go by. And it says a sample of coal certified by the NIST contains 3.19% by weight of sulfur. So this is a standard that the company has ordered. They have received the coal sample in the laboratory, and the COA basically says this is 3.19% sulfur. So that way when we do our testing, we should get something close to 3.19. But, you know, we know it's not going to be perfect. We know we're not going to get the true answer. We can get close, but probably we can't be spot on. So are we confident enough with our numbers to go forward with the testing? That's what this is all about. So it says you're testing a new analytical method to see whether it can reproduce the known value. So this company's come up with a new way, maybe a better way to do the test. Maybe it's least intrusive. Maybe it's a little bit easier for you as far as the number of steps go. Maybe it's doing away with some dangerous chemicals that they don't want you exposed to. Whatever the case is, it's a new method. And it says this method gave us these values: 3.29, 3.24, 3.30, and 3.25 sulfur. Does the answer agree with the known answer? Well, before we do any calculations at all, we can already see that these values are a little high. Every single time they were a little high, right? 3.29, 3.24, 3.30, 3.25, all of those are higher than the 3.19 that is accepted. But we know there's error. We know it's going to happen, whether it's low, whether it's high, whether it's in between, who cares? We know the error is going to be there. So the take-home message is this good enough? We know it's all a little bit high, but is it too high for us to report? Or is it just slightly higher and it's okay to go on with the method from that point on? You know, what do we do? How do we handle this type of information? All right, so what we do is we use the student t value and we go through the student t equation the same as before. So I take the average, I take my t, I take my s, and I take my n. So let's go ahead and write that down onto a sheet of paper. So x bar plus or minus ts over square root of n. All right, well, I need a average here. And the average is listed in the PowerPoint, but again, I will go through and do it all over. So I'll just delete all of this mess. And we've got 3.29 and 3.24, 3.30, and 3.25. And I want the average, so equal the word average, open the parentheses up, highlight the data and hit enter. So there is the average. I'll just write average beside of it so I know what it is. And then standard deviation. So equals STDEV, open the parentheses up, highlight the data, hit enter, and this is my standard deviation. All right, so those are the two numbers that I need for the equation. 3.27 is the average. So I'll come here, 3.27 plus or minus. My t-value I don't know yet. I'll get that here in a minute. My standard deviation I just calculated, right? 0.03 basically. Let's round it off. Two numbers. The reason I do two numbers here is because that's two numbers there after the decimal. So I need a t number and I need the square root of n. So how many numbers or attempts did we do? We did 4. So square root of 4. So I need my student t number. Here in the problem, notice it didn't really say. It just says, does it agree with the answer? It doesn't give me a confidence interval to go by. So by default, I do what? 95. So I'll go to the 95 column. Here we are. There's 4 measurements. So 4 minus 1 is 3 degrees of freedom. So I go to 3 and I come over to 95. And it looks like the number that I used here is 3.182. So 3.182 goes in for my student t. All right, so I'll take my 3.27 plus or minus, let's use my calculator here, 3.182 times 0.3, and then I'm going to divide that by the square root of 4. Well, the square root of 4 I can do in my head. That's a 2. And that gives me a 0.47. Okay, so 3.27 plus or minus 0.4, and I'm just going to round it off to 0.48. And you know what? That is a mistake. And the reason is because this is not a 0.3, this was a 0.03. So that's going to change this number down here. Thank you if you caught that. You were probably screaming at me in the computer screen. All right, so this is a 0.03, right? My standard deviation is 0.03, not 0.30. I got that backward. All right, so let's try this again. This is going to be 3.182 multiplied by 0.03, and then we're going to divide that by the square root of 4, which is a 2. Hit enter, and that gives me a 0.047. And I'm going to put the little 7 down here below, just to let you know that it's there. Significant figure-wise, though, we'll worry with that later. But rounding errors, just in case I want to keep extra digits, that's what I'll do. The question is, do I put this as a 0.04, or do I round this up to a 0.05? You know, will it change my answer either way that I do it? And that's the reason that I put the 7 as a really small subscript there, just so I can go back and count it if I want to count it in to see if there is a change. All right, so this is my confidence interval, 95% certain. So that means when I took this coal sample, I'm 95% certain that the true value lies within this window range. So 3.27 minus 0.047, that gives me 3.223, all the way up to, and this is 3.27 plus 0.047, and that gives me 3.317. So I'm going to report my value as this. I'm 95% certain that the true value lies within this range, 3.22 to 3.31. And the lab is going to come back and they're going to say, you know what, Tracy, you're wrong. We're sorry. Something either happened with your measurements or with your technique, or something is wrong with the method that we are testing, but something is off. Because we know, because we ordered this standard from a company, that your answer should be 3.19. That is the accepted true answer. And based on the data that you're giving us, 3.19 falls outside of this window. And because it falls outside of the window, your answers are incorrect. We cannot report these numbers. It doesn't include the accepted value. So that means until we find something that is wrong, until we find the piece that's throwing the numbers off, we cannot use this method because it is not reliable. And this is another way that a laboratory will use something like confidence interval when they report their data. So again, this is a calculation that we often do. Most of the time in a lab, though, you key in your numbers and they have computer software that will do the calculations for you, but don't take it for granted. Right? It's very important that you understand your multiplication tables before you use a calculator. Right? A calculator is a tool that will do it for you, but it's really important for you to understand where those numbers are coming from. The same thing is happening here. It's really important for you to understand where these software systems are pulling numbers from and what they mean. And this is a true case of what goes on in a laboratory environment. So, 3.19 was accepted. Your data, based on all of your values, we knew were a little bit high, but was it good enough to pass? And the answer is no. We're going to have to go back, figure something out, or not use the method at all because it's not working. It does not include the actual value that is accepted because we ordered this from a company that told us this is the true value. All right, so that's the second case of using confidence limits. One, I want to report a range just so people know working ranges. Two, here's a case where we know what the true value is. We are testing a new method that we are doing in a lab, or we are testing a new employee that we have brought into the lab to see if they are actually making sense with their lab measurements, their transfers, their reporting, and their results. So it's not the only time that we use confidence limits. These are not the only calculations that we'll talk about. There's more. But this will get your feet wet, and this will get you started in the world of statistics. Again, statistics chapter can be found in the textbook, Analytical Chemistry in a GMP Environment. So read that chapter if you're having trouble with it, as far as the theory is concerned at least. They'll go through a little bit of statistics and they will help you out.